Assalamualaikum, good day. In 6.1, we learned the definition of the Laplace transforms, and we also learned how to use the table of Laplace transforms to find the Laplace transforms of some basic functions. In this section 6.2, we are going to discuss the inverse Laplace transforms. If the Laplace transform of f of t is fs, okay, so this is how we write the Laplace transform of f of t, capital letter L. Inside the square bracket, we write f of t. So Laplace transform of f of t is equals to fs. Then the inverse Laplace transform of fs is f of t. So this is how we write the inverse Laplace transform. We write capital letter L, superscript -1, and inside the square bracket, we write f of s. So the inverse of fs is equals to f of t. So Laplace transform of f of t is equals to fs. So the inverse Laplace transform of fs is f of t. This is the table of Laplace transform, and this table gives us the list of 8 functions which are commonly used in differential equations. And all these functions are expressed in terms of t, f of t. In the right column, you see the Laplace transform of those functions, and they are all expressed in terms of s. Laplace transform of f of t is equals to fs. For example, Laplace transform of t is equals to 1 over s squared. So this is a function in terms of t. Okay, when we get the Laplace transform, it is in terms of s. This is in s. Laplace transform of sine kt is k over s squared plus k squared. The Laplace transform of sinh kt is k over s squared minus k squared. So Laplace transform f of t is equals to fs, implying that the inverse Laplace transform of fs is equals to f of t. Okay, so when you want to find the inverse Laplace transform of a function in s, the result will be in terms of t. For example, the inverse Laplace transform of 1 over s squared is equals to t. The inverse Laplace transform of 1 over s minus a is equals to e to the power of at. The inverse Laplace transform of s over s squared plus k squared is equals to cos kt. So let us now try to answer some problems. Question number 1. What is the inverse Laplace transform of 1 over s minus 2? To get the answer for this problem, we just have to match this expression with one of those given in the table. So it seems that the formula at row number 4 exactly match with what we are seeing here. 1 over s minus 2, 1 over s minus a, meaning that in this problem a is equals to 2. Now since the inverse of 1 over s minus a is equals to e to the power of at, and therefore the inverse Laplace transform of 1 over s minus 2 is equals to e to the power of 2t. Okay, we just have to replace a by the number 2. Okay, so this is the function in s. After we have found the inverse of the function in s, the answer is in terms of t. Question number 2. What is the inverse of 6 over s to the power of 4? The denominator contains a factor of s to the power of 4. Okay, so you compare with one of those formulas given in the table. So it seems that this expression matches with the one given at formula row number 3. S to the power of 4. 4 is the same as n 3 plus 1. So that means n must be equal to 3. Okay, so s to the power of 3 plus 1, s to the power of 3 plus 1. And according to the formula, the numerator must contain the number n factorial. Now since n is equal to 3, so the numerator has the number 3 factorial. Now indeed 6 is equals to 3 factorial. So this expression now matches the form shown at formula row number 3. So since n is equal to 3, so we can say that the inverse Laplace transform of 3 factorial divided by s to the power of 3 plus 1 is equal to t to the power of 3. Okay, just replace n by the number 3. Question number 3. What is the inverse Laplace transform of 4 over s squared plus 16? Okay, so if you try to compare this expression with one of those listed in the table, it seems that formula number 5 exactly match with what we are seeing here. This is a constant k is equals to 4, and k squared, 4 squared is 16. Alright, so since the inverse Laplace transform of k over s squared plus k squared is sine kt, therefore the inverse Laplace transform of 4 over s squared plus 16 is equal to sine 4t. K has been replaced by the number 4. Find the inverse Laplace transform of s over s squared minus 3. So comparing with one of those formulas listed in this table, it seems that this expression matches with the one given at formula row number 8. Okay, s over s squared minus k squared. So k squared in this problem is given by the number 3. So if k squared is equal to 3, therefore k must be square root of 3. So just substitute square root of 3 into the formula of this inverse transform. So the inverse Laplace transform of s over s squared minus 3 is equal to cos square root of 3t. Cos kt, k is equal to square root of 3. Linearity of the inverse transform. The inverse Laplace transform is a linear operation because of the linearity of the Laplace transform itself. Okay, so in section 6.1, we have learned the linearity of the Laplace transform. For constants a and b, the inverse Laplace transform of a fs plus b gs is equals to a inverse Laplace transform of fs plus b times the inverse Laplace transform of gs. So this means that if you want to find the inverse Laplace transform of a sum of two functions in S, it is equals to the sum of the inverse Laplace transform of each of the function in S. At the same time, if you want to find the inverse Laplace transform of a constant multiplied by the function in S, that would be the same as the constant multiplied by the inverse Laplace transform of that function in S. Example, evaluate the inverse Laplace transform of 2 over s squared minus 3 over s plus 6 plus 4 over s squared plus 1. So to answer this question, we are going to apply the linearity of the inverse transform. Okay, so you have to split this into 3 different problems of inverse transforms. So you get inverse transform of 2 over s squared minus the inverse transform of 3 over s plus 6 plus the inverse transform of 4 over s squared plus 1. You can also do the following. Okay, inverse transform of 2 over s squared. Now 2 is a constant, so you can take the 2 out. So it will be 2 times the inverse of 1 over s squared. And minus inverse transform of 3 over s plus 6. So 3 can be taken out from this expression. So you get negative 3 inverse of 1 over s plus 6 plus, and then the inverse of 4 over s squared plus 1. 4 take out of this expression. So you get 4 times the inverse transform of 1 over s squared plus 1. So after this, you can search these answers of the inverse Laplace transform from the table of Laplace transform. So we know that inverse of 1 over s squared is equal to t. So for the first part, the answer will be 2 times t minus 3 times the inverse of 1 over s plus 6. Refer to formula row number 4 from the table of Laplace transform, where we have the inverse of 1 over s minus a. So in this case, a must be negative 6. So the answer will be negative 3 e to the minus 6t. Okay, a has been replaced by the number negative 6. Plus 4 times the inverse Laplace transform of 1 over s squared plus 1. So this formula here, or this expression here, matches with formula number 5 in the table of Laplace transform, where k is equals to 1. So the answer for this inverse will be sine kt, k equals to 1. So plus 4 sine t. Okay, so the result for the inverse of this function is given by 2t minus 3e to the minus 6t plus 4 sine t. The finding of the inverse Laplace transforms may not be as straightforward as the ones illustrated in the previous examples. What if the fs given in the problem does not exactly match with the ones given in the table of Laplace transforms? So what do we do? Let us discuss some approaches that we can apply in order for us to solve the problem of finding the inverse Laplace transforms. First situation, if the given fs does not exactly or but closely match with the form from the table of Laplace transform, then it may be necessary first to manipulate fs without altering its originality. This could be done by multiplying and dividing the function by an appropriate constant. In the process of solution, apply linearity of the inverse wherever possible. I will explain this by showing an example of a problem. So let us try to evaluate the inverse Laplace transform of 1 over 4s minus 1. If you look at this expression does not match any of the formula given in the table of the Laplace transform. But this expression closely match with the one shown at formula row number 4. The inverse of 1 over s minus a is e to the power of at. But what we have here is the inverse of 1 over 4s minus 1. The formula at row number 4 says that the constant multiplied by s is the constant 1. But here, there is the constant 4 instead of 1. So how to eliminate this constant 4? What we want is a constant 1 multiplied by the s. So an approach that we can apply is as follows. We factor the number 4, so that in this bracket we have this expression 4 times s minus 1 over 4. Now how do we get this? After factoring the number 4, 4 times s, we get back the original function for s minus. Now why do we have to take 1 over 4 here? Because 4 multiplied by 1 over 4 gives back 1. So remember, when we want to manipulate the fs, we must make sure that we do not alter the original function. Okay, so if we have factored the number 4, to get back the original function, 4 must be multiplied by s minus a quarter. 4 times s is 4s minus 4 times a quarter is 1. Okay, after having done this, 1 over 4 is just a constant. By the concept of linearity of the inverse Laplace transform, we can factor the quarter. So take the quarter out. So a quarter multiplied by the inverse Laplace transform of 1 over s minus a quarter. So this expression here now exactly matches with the one shown at formula number 4, 1 over s minus a. This time a is equals to a quarter. So the result for this inverse Laplace transform is a quarter multiplied by the inverse of all this, which can be obtained by this formula, e to the power of a quarter t. Okay, a has been replaced by a quarter. The next problem, find the inverse of 5 over s squared plus 9. Search from the table of Laplace transform and find out which formula exactly match or closely match the one given here. It seems that formula number 5 closely match with the one given in the problem. Formula number 5 says the inverse of k over s squared plus k squared is equal to sine kt. Notice that the denominator contains a factor of k squared and the numerator contains the number k. So if this is k squared, up here must be k. Now let's look at the given problem. This is 9. 9 is the same as 3 squared. So by right, to apply formula number 5, if this is the number 9, then number 3 must appear at the denominator. But unfortunately, this is not number 3, but it is 5 instead. So how do we manipulate this given function in order for us to be able to apply formula number 5? The first thing that we can do is to apply the linearity of the inverse transform. We know that 5 is 5 multiplied by 1, so why don't we take out the number 5 and leave 1 inside. Okay, 5 multiplied by 1 gives back the number 5. So we get 5 times the inverse of 1 over s squared plus 9. Next thing is to apply formula number 5. If this is the number 9, then there must be a number 3 above here. So why don't we write the number 3 up here? Okay, now if we have placed the number 3, then we have altered the original function. Originally, this must be number 1, but now we have replaced it by the number 3. So we have changed the original function. To get back the original function, we need to divide back by 3. So you write down 5 over 3. Because 3 divided by 3 gives back the number 1. Or we can say 5 over 3 multiplied by 3 gives back the number 5. Okay, so we have a constant 5 over 3 multiplied by the inverse of 3 over s squared plus 9. So to find this inverse, you can now use formula number 5 directly, where k is equal to 3. So the answer is 5 over 3 sine 3t. Next question. Find the inverse of 1 over s minus 2 over s cubed squared. So firstly, we have to square this given function. We can apply the formula a minus b squared is equals to a squared minus 2 times ab plus b squared. Okay, so for the first term, when you square it, you get 1 over s squared minus 2 times the first term times the second term, that gives 4 over s to the power 4 plus the square of the second term, that gives 4 over s to the power 6. Now apply the concept of linearity of the inverse transform, where we can split this into 3 problems of inverse functions. So you get inverse of 1 over s squared minus the inverse of 4 over s to the power 4. But 4 is 4 multiplied by 1, so you can take out the number 4 and leave 1 inside. So minus 4 times the inverse of 1 over s to the power 4 plus the inverse of 4 over s to the power 6. Now 4 is 4 multiplied by 1. Take out the number 4, leave 1 inside. So 4 multiplied by the inverse of 1 over s to the power 6. So we have 3 inverse problems to compute. For the first one, we can easily use formula number 2 from the table of Laplace transform. Okay, where we know that the inverse of 1 over s squared is equal to t. So this answer can be obtained directly from formula number 2. What about the inverse of these two functions? Okay, so searching from the table of Laplace transform, it seems that these two almost match or closely match with the ones given at formula number 3. Now, the denominator for this part is s to the power of 4. S to the power of 4 meaning s to the power of 3 plus 1 n is equal to 3. So by right, there must be a 3 factorial at the numerator, and unfortunately there is no 3 factorial at the numerator. Similarly, for this part here, s to the power of 6, meaning s to the power of 5 plus 1. So by right, 5 factorial must appear at the numerator. Unfortunately, there is no 5 factorial at the numerator. So we need to manipulate these two functions in order to be able to use formula number 3. Okay, so to apply formula number 3, for this factor here, s to the 4 is s to the power of 3 plus 1. So why not we write down 3 factorial to follow this formula? Okay, but we have changed the original number. Originally the number here is 1, but this is 3 factorial. To get back 1, we need to divide back by 3 factorial. Okay, so 3 factorial divided by 3 factorial gives back the number 1. Or we can say 4 divided by 3 factorial multiplied by 3 factorial gives back the number 4. What about this part here? Okay, so s to the 5 plus 1, write down 5 factorial, and to get back the number 1, we need to divide back by 5 factorial. 5 factorial divided by 5 factorial gives back the number 1, or we can say 4 over 5 factorial multiplied by 5 factorial gives back the number 4. Okay, so after we have done this, we can now apply formulas 2 and 3. Okay, so for the inverse of 1 over s squared, the answer is certainly t minus 4 over 3 factorial, 4 over 6. When you reduce it, you get 2/3. Inverse of 3 factorial, s to the power of 3 plus 1, apply formula number 3. Now n is equal to 3, so the answer is t cubed. So negative 2/3 t cubed plus 4 over 120 becomes 1 over 30 times the inverse of 5 factorial over s to the power of 5 plus 1. This can be taken from formula number 3, where n is equal to 5. So the answer is t to the power of 5. Okay, so the result for this inverse is t minus 2/3 t cubed plus 1 over 30 t to the power of 5. Another situation is when the given fs is a rational function that incorporates sums or differences in the numerator and possibly at the denominator too, where the denominator cannot be factored. The approach is to apply termwise division before evaluating its inverse. Find the inverse of 2s minus square root of 3 divided by s to the power of 4. This is a rational function. The numerator contains a difference of two terms and there is only a single term at the denominator. So we are going to apply termwise division. Take the first term divided by the denominator minus the second term divided by the denominator. So this is equal to the inverse of 2s divided by s to the power of 4 minus the inverse of square root of 3 divided by s to the power of 4. But 2s over s to the 4th is the same as 2 over s cubed. And for the second term, square root of 3 is the same as square root of 3 multiplied by 1. So we can take out the square root of 3, leave 1 inside. So now that we have two inverse problems to compute. So it seems that formula number 3 can be applied to get the inverse of these two functions. Okay, now for the first inverse problem, we do not have to manipulate the function at all because this expression here exactly matches with the one given at formula number 3. Because s to the power of 3 is the same as s to the power of 2 plus 1, and by right there must be a 2 factorial at the numerator, and 2 factorial is exactly equals to 2. Okay, so we don't have to use formula, we don't have to manipulate this function at all. So the inverse of 2 over s cubed is given by t squared minus square root of 3 times the inverse of 1 over s to the power of 4. Okay, so s to the power of 4 is the same as s to the power of 3 plus 1. Write down 3 factorial at the numerator, and to get back the original number, we have to divide back by 3 factorial. Okay, so root square root of 3 divided by 3 factorial multiplied by 3 factorial gives back square root of 3. And now we can apply formula number 3 to get the inverse of this function. So inverse of 3 factorial over s to the power of 4 is equals to t cubed. And the constant at the front of 3 cubed is square root of 3 divided by 6. Because 3 factorial is 6. Another question, find the inverse of s minus 4 divided by s squared plus 2. So notice that the denominator cannot be factored. So what we are going to do is to apply termwise division again. So inverse of the first term divided by the denominator minus inverse of the second term divided by the same denominator. So inverse of s divided by s squared plus 2 minus inverse of 4. Now 4 is the same as 4 multiplied by 1 divided by s squared plus 2. Okay, so that will be equals to. Now how to find the inverse of these two functions? We need to refer to the table of Laplace transform, where we can apply firstly formula number 6 to answer this inverse problem. Okay, so here we can apply formula number 6 directly. S over s squared plus k squared. Okay, notice that k is equals to square root of 2. Alright. But for the second inverse, we are going to apply formula number 5. Okay, k over s squared plus k squared. But this is not k. If k squared is 2, by right there must be a square root of 2 at the numerator. Okay, so we're going to write down square root of 2 at the numerator and divide back by square root of 2. So after doing so, we can start finding the inverse Laplace transform of these two functions. Okay, so for the first one, we can apply formula 6 directly. So k is equal to square root of 2, so the answer will be cos square root of 2t minus, and for the second inverse, 4 over square root of 2 multiplied by the inverse of this function based on formula number 5, the answer will be sine square root of 2t. The next situation is when the given fs is a rational function and its denominator is factorable into distinct factors. The approach is to decompose the function into a sum of partial fractions before evaluating its inverse. Example, find the inverse of s plus 1 divided by s squared plus 5s plus 6. Now this is a rational function and the function at the denominator is quadratic. It is of degree 2 and this function can be factorized. S squared plus 5s plus 6 is equals to s plus 2 multiplied by s plus 3. So notice that the denominator contains a product of two linear factors. Both s are of degree 1. So in order for us to evaluate the inverse of this function, it is important that we apply partial fraction first. Okay, so let me illustrate to you how to apply the partial fraction. Alright, so s plus 1 divided by s plus 2 multiplied by s plus 3. We are going to decompose this into a sum of two partial fractions because there are two linear factors at the denominator. So this is equals to a over s plus 2 plus b over s plus 3. So we need to find the values of a and b, and here I am using the cover-up method, which I have already explained to you in class before. Okay, so we write down to find the a, we write down the expression on the left side. A is equal to s plus 1 divided by s plus 2 multiplied by s plus 3. To find a, we need to cover the factor s plus 2 since a is above s plus 2. Okay, so you cover the s plus 2. So when we cover this, we are trying to imply that this factor is equal to 0. So if this factor is equal to 0, that means s must be negative 2. Then substitute negative 2 into the s which are not covered. So negative 2 plus 1 gives negative 1. Negative 2 plus 3 gives 1. That means a is equals to negative 1. We apply the same approach to find the b. Okay, so b is equals to, now write down the same expression as on the left. By using the cover-up method, since b is above s plus 3, we need to cover s plus 3. When we cover s plus 3, we are implying that this factor is assumed to be 0. So if s plus 3 is equal to 0, that means s equals to negative 3. Substitute negative 3 into the two s which are not covered. Okay, so negative 3 plus 1 gives negative 2. Negative 3 plus 2 gives negative 1. That means b is equal to 2. Okay, so we know that a equals to negative 1, b equals to 2. Replace a and b by the numbers that we have just obtained. So it will be negative 1 divided by s plus 2 plus 2 over s plus 3. So this rational function now can be replaced by this expression. Okay, so transfer this result back into the inverse problem. So we shall write as follows: inverse of, okay, negative 1 over s plus 2 plus 2 over s plus 3. Okay, because we have said that these two are equal based on partial fraction. Once we have done that, we can split this into two different inverse problems based on the linearity of the inverse functions. Okay, so you have inverse of 1 over s plus 2, so you can take negative 1 out, plus, and then the 2 you can take out of this inverse, so 2 multiplied by the inverse of 1 over s plus 3. And the result for this can be obtained by applying formula number 4. So inverse of 1 over s minus a is e to the power of at. So for the first inverse, a is equals to negative 2, and for the second inverse, a equals to negative 3. So the result is negative e to the negative 2t plus 2e to the negative 3t. Find the inverse of s minus 2 divided by s times s squared plus 3. This is a rational function and the denominator contains a product of two factors. One of these is a linear factor s of degree 1 and the other is quadratic s of degree 2. To find the inverse of this function, we must firstly decompose this into a sum of partial fraction because the denominator contains a product of two different factors. Okay, so let us do the partial fraction. Okay, s minus 2 divided by s times s squared plus 3. So since the first factor here is of degree 1, so we simply write the partial fraction as a over s plus, and for the second factor, since this is of degree 2, so the partial fraction that relates to it must be bs plus c divided by s squared plus 3. Notice that if the denominator is of degree 2, then the numerator must be of degree 1. Okay, so this is quadratic, the numerator must be linear. So now there are three unknown constants a, b, c that we need to find out their values. Okay, so since there is a product of a linear as well as a quadratic factor, so we cannot rely totally on the cover-up method, because the cover-up method is applicable if both of these are linear factors. So between s and s squared plus 3, the common denominator will certainly be the product of these two, which will be s times s squared plus 3. Okay, whatever we write on this right side must be the same as the one written on the left side, because this is equal. Okay, so a multiplied by s squared plus 3 plus bs plus c multiplied by s. So since this is equal, the left side is equal to the right side, it shows that the left numerator must also be the same as the right numerator. Okay, so a times s squared plus 3 plus bs plus c times s is equals to s minus 2. Open up the bracket, we get as squared plus 3a plus bs squared plus cs equals to s minus 2. And let us group the terms with the same powers of s. So we get a plus b multiplied by s squared plus 3a plus cs equals to s minus 2. Compare the left side with the right side to get the unknowns a, b, c. So the first thing that we can see is the value for the c. On the left side, the coefficient of s is equal to c. On the right side, the coefficient of s is equal to 1. So certainly c equals to 1. Next is to get the coefficient of a, then the constant a. Because on the left side, the constant term is 3a. On the right side, the constant term is negative 2. So 3a equals to negative 2. That means a must be negative 2 over 3. And for the coefficient of s squared, a plus b is the coefficient of s squared on the left, but there is no s squared on the right side. That means the coefficient of s squared on the right side is equal to 0. So if a plus b equal to 0, b must be negative a, but we already know the value of negative a, therefore b must be equals to 2/3. Okay, substitute these values a, b, c back into the partial fraction. So this is what we are getting. Inverse of a over s. Now a is negative 2/3 plus bs plus c. Now b is known to be 2/3. So bs plus c is 1 divided by s squared plus 3. Okay, so this is the inverse problems that we need to compute. And now we're going to apply the linearity of the inverse Laplace transform. We split this into 3 parts, 1, 2, 3. So for this term, we need to take the first term divided by the denominator plus the second term divided by the same denominator. Okay, so this is what we are getting, inverse of negative 2 over 3s. So negative 2 over 3, the 3 can be placed at the denominator. So negative 2 over 3s plus 2 over 3s, so 2s. So 2s placed at the numerator and bring 3 down at the denominator. So 2s over 3 times s squared plus 3 plus 1 divided by s squared plus 3. Okay, so we have 3 inverse problems to evaluate and get the inverse problems of those functions by looking at the table of Laplace transform. Okay, so for the first one, we can take the constant negative 2, 3 out of the inverse problem. So negative 2 over 3 times the inverse of 1 over s. Plus, and for the second inverse, we can take out the constant 2/3. So 2/3 inverse of s. Okay, leave s inside. S divided by s squared plus 3 plus inverse of 1 over s squared plus 3. Alright, so it seems that we are going to apply formula number 6 to get the inverse for this function. Okay. And formula number 5 to get the inverse of this function. Alright, so inverse of 1 over s, you can get it directly from the table, which is formula number 1. So negative 2/3 times 1, it will be negative 2/3 plus 2/3. Okay, inverse of s over s squared plus 3, we can get it directly from formula number 6, where k is square root of 3. So substitute k by square root of 3 to this form here. So it will be 2/3 cos square root of 3t plus, and for the last one here, we need to do some manipulation. If we are going to apply formula number 5, if there is a number 3 at the denominator, at this part here, so there must be a square root of 3 at the numerator. So put square root of 3 in here and divide that by square root of 3. So that's what we get, 1 over square root of 3 sine square root of 3t. Before I end this lesson, let me point out some mistakes that are commonly made by some students. These are some examples of questions. Find A, the Laplace transform of sine squared t. Now sine squared t is the same as sine t multiplied by sine t. Is it true that the Laplace transform of sine squared t is equals to Laplace transform of sine t multiplied by the Laplace transform of sine t? No, it is not true. This answer is incorrect. Okay, why is it incorrect? Because there is no theorem that says the Laplace transform of a product of two functions is equal to the Laplace transform of the first function multiplied by the Laplace transform of the second function. Okay, so this work is incorrect. So how do we solve the Laplace transform of sine squared t? I've already shown you the solution for this kind of problem in section 6.1. To solve this problem, we have to find the trigonometric identity that relates to the function sine squared t. Okay, after we have found the trigonometric identity, then we continue to find the Laplace transform of the given function. What is the inverse of 3 over s multiplied by s squared plus 4? Now 3 is the same as 3 multiplied by 1. Is it true that the inverse of 3 over s multiplied by s squared plus 4 is equal to the inverse of 3 over s multiplied by the inverse of 1 over s squared plus 4? Is this statement true? No, it is not true. This statement is incorrect. It is not true that the inverse of the product of the first function with the second function is equal to the inverse of the first function multiplied by the inverse of the second function. So this work is totally incorrect. So how to find the inverse of this kind of function? Okay, this function here is similar to the function that we have discussed in the previous slide. Notice that the denominator is a product of linear factor and a quadratic factor, so we have to decompose this into a sum of partial fractions, find the partial fraction decomposition of this expression of the function, and from there we continue and find the inverse Laplace transform. Okay, so these are some of the mistakes that have been made by students in the past, so please do not repeat the same mistakes. So this is the end of today's lesson, and we will discuss 6.3 after this. So thank you for your kind attention.